Hi everyone, in this video I'll teach you how to work with continuous time signals and systems through some very simple exercises. I'm Giovanni Geraggi, but everybody calls me Gio. I'm an expert in wireless communications and an assistant professor at UPF in Barcelona. I keep posting theory and tutorial classes on signals and systems, so if you want to nail your signals and systems exam, or if you're simply interested in this topic, check out the other videos on my channel. So now let's get started. The first exercise we'll do today asks to write two formulas for this signal x of t, one as a sum of step functions and another as a product of step functions. If you don't know what a step function is, I recommend watching my theory videos where I explain step functions and many other concepts. So how to solve this exercise? Well, first of all, I'm going to draw a representation of the signal x of t. So as you can see, x of t is 1 between a and b and 0 elsewhere, right? So it has a rectangular shape. So if we want to represent this as a sum of step functions, we're going to need a step function that is 1 from a onwards and another step function that is 1 from b onwards. This is because if we subtract the second one from the first one, then what we obtain is the resulting x of t that we're looking for, which is 1 only between a and b. So if we write this in formulas, x of t will be given by u of t minus a minus u of t minus b. So 1 between a and b and 0 elsewhere. So let's try to do the same thing, but as a product of step functions now. So we can reuse the same first step function, u of t minus a, but we're gonna need another step function now, which is reversed, so it's u of b minus t. It is a step function that is 1 between minus infinity and b and 0 elsewhere. So if we make a product of these two, the resulting signal x of t is going to be 1 only when both of them are 1, only when both of them are non-zero, which is between a and b. So again, x of t is given by u of t minus a times u of b minus t. Cool. Here's the second exercise we'll work out today. So we are given several expressions that we need to simplify. Basically, we need to make several calculations. Notice that some of them are convolutions, indicated with a star, and others are usual products, so usual multiplications. If you're not familiar with the convolution operation, I suggest that you watch some of my theory classes where I define the convolution and give some examples. But let's move on. So let's start with part A of this exercise. So in part A of this exercise, we need to calculate the convolution between delta of t minus 10, which is a delta centered in 10, and this expression in square brackets, which is delta of t plus 10 plus 2 e to minus t u of t. So how to do that? Well, we can use the distributive property and calculate this as two different convolutions. So we distribute the content in the square brackets and we come up with two different convolutions. So a delta of t minus 10 convolution, delta of t plus 10, and a second convolution. How to solve this? Well, we recall that convolution by a delta is equivalent to shifting the original signal. So when we do a convolution between delta of t minus 10 and delta of t plus 10, the result is going to be delta of t, because the second signal is shifting the first one by a quantity 10, so it's replacing it back onto 0 at the origin. The same thing happens for the second convolution, so the signal in the square brackets gets shifted by a quantity minus 10, and therefore the resulting signal is the shifted version, so it's 2 e to minus t minus 10 u of t minus 10. Let's now work on part B of the exercise. So now we have the product between a cosine and a sum of deltas. Again, we use the distributive property and we rewrite this as two different operations that we then add up. Now we're going to use the sampling property of the impulse of delta of t, which says that when we multiply a signal by a delta, the result is going to be the same delta times the value of the signal where the delta is positioned. In this case, the first delta is positioned at t equals 0, and the second delta is positioned at t equals 0.02. So here's what happens. The first cosine will be evaluated at t equals 0 and the second cosine at t equals 0.02. Then we can further simplify these expressions because cosine of 0 is 1 and cosine of a multiple of 2 pi, of an integer multiple of 2 pi, is also 1. So here's what we get as a result. In the end, we obtain delta of t plus delta of t minus 0.02. In this exercise, we need to calculate the derivative of a product between two signals. So as you know, this can be calculated as the derivative of the first one times the second one plus the first one times the derivative of the second one. So the first part is quite straightforward because the derivative of an exponential is something we're all familiar with. What about the second part? I had to calculate the derivative of u of t minus 2. U of t minus 2 is a step function centered at time equal 2. That's where the discontinuity is. So the derivative of this step function is the ideal impulse delta of t minus 2 centered at the same spot. So finally, by applying again the sampling property of the impulse to the second part of the expression, I evaluate the exponential at t equal 2, and finally I obtain this compact expression where the first term is minus 2 e to minus 2t minus 2 u of t minus 2, and the second term is simply a delta centered at 2 because the exponential evaluated at t equal 2 returns 1. In this exercise, I need to calculate an integral. So it's the integral of a product between a cosine and a sum of deltas. So how to do this easily? Again, we can use the distributive property, and we therefore decompose the integral into two integrals. So we can try to solve them separately, which is probably easier. And we're going to use again the sampling property of the delta. So we can simply evaluate the cosine at tau equals 0, the first cosine, and the second cosine at tau equals 0.02. So by further simplifying this, we have that the cosines are worth 1, both of them. And so we come up with two integrals of the deltas. And the integral function of a delta is a step function, as you might recall. So the first integral gives u of t, and the second integral gives u of t minus 0.02. In this exercise, we need to calculate the convolution between three different impulses, and we can do this in different ways. Because of the associative property, we can first do the convolution between the first and the second one, and then convolution of the result with the third one, or vice versa, or in any other order. In this case, I choose to do convolution of the first two, and then with the third one. So the convolution between delta of t minus 1 and delta of t minus 2 is going to be delta of t minus 3 because of the shifting property of the delta in a convolution operation. And when I do convolution with delta of t, this is the identity of the convolution product, so I get delta of t minus 3. In part F of the exercise, I need to do a product now between an exponential function, a step function, and a delta. How to do that? I use the sampling property of the impulse again. So I evaluate everything at t equals 5, and this is what I obtain, and then I can simplify. And by knowing that u of 1 is 1, because the step function is 1 for positive times and 0 for negative times, I further simplify the expression and I obtain 1 over e times the delta centered at 5. Let's move on. In this case, we need to calculate the integral of a delta. And how do we do that? Well, we know that the integral of the delta is a step function, so it would be u of tau minus 1, which I need to evaluate between minus infinity and t minus 5. So I get u of t minus 5 minus 1 minus u of minus infinity. We know that u at minus infinity is 0 because u is 0 for negative times. So the result is simply u of t minus 6. Part H asks us to calculate the product between an exponential, a step function, and some deltas. Again, I use the distributive property. So I obtain two different products. And because there's a product with a delta, once again, we use the sampling property of the impulse. So we evaluate the first expression at t equal -1 because it's multiplied by a delta of t plus 1, and the second one at t equal +1. So this is what I obtain, and again, by recalling that u is 0 for negative times and it's 1 for positive times, I further simplify this and I obtain e to -4 delta of t minus 1 as a final result. Now part I, which was the last part of this exercise, is the integral of a product of an exponential, a step function, and an impulse. How to do that? Again, I apply the sampling property of the delta, which means that because these are functions of tau, because it's an integral in d tau, I need to look at delta of t minus tau as a function of tau. And so it's basically an impulse centered at tau equal t. That means that I need to evaluate e to -4 tau and u of tau at tau equal t. This is what I'm doing in the second line, so I've rewritten the integral by having e to -4t u of t, okay? But now these functions, e to -4t and u of t, are not functions of tau anymore, so they can be taken out of the integral. The integral that is left is simply the integral of a delta, which we know is 1 because the area of a delta is 1. Thus the result is simply e to -4t u of t. Let's move on to the third exercise now. So here what we need to do is to use the convolution integral to calculate the output of a certain system. Okay, so in this case, x of t is the input of my system, h of t is the impulse response of the system, and as you may recall, the output y of t will be given by the convolution between these two. So we have 4 different cases. Let's get started. So in the first part of the exercise, both the input and the impulse response are simply step functions, u of t. So if I want to calculate the output, I need to do the convolution between them, which is the convolution between two step functions. And we know that this is the integral of u of tau, u of t minus tau d tau, because the convolution is the integral between x of tau times h of t minus tau d tau, right? So how to calculate this integral? Again, let's look at when the step function is non-zero. So the step function u of tau is 1 for positive tau. So I can simply rewrite the integral by changing the integration boundaries, and now I have the integral that runs between 0 and infinity. So I have got rid of the first u of tau. I do the same thing with the other step function by noticing that u of t minus tau is 1 when tau is smaller than t, right? So again, I can rewrite the integral, and this time the integral runs between 0 and t, because as we saw, tau has to be larger than 0 and smaller than t. So how much is this integral? Well, this integral is simply t when t is positive, and it's 0 when t is negative, because there's nothing to integrate over. So the result can be written in a compact way as t times u of t. So it would be t for positive t, but 0 for negative t. Cool. The second part of the exercise, in part B, now the input of my system and the impulse response of the system, they're both right-sided exponentials. So they are given by e to -at u of t. So how to calculate the output? Again, it's going to be the convolution between input and impulse response. And let's calculate this convolution with an integral. So here's what I get by writing the integral of x of tau times h of t minus tau in the tau. How to solve this integral? Well, like previously, I recall where the step functions are non-zero, and so I reduce the integral to an integral that runs now between 0 and t of the product of those two exponentials, and then I can group the two exponentials by summing up their respective exponents, and I end up with the integral between 0 and t of e to -at in the tau. I notice again that e to -at does not depend on tau, so it's a constant for the integral and can be taken out, and I obtain e to -at, the integral between 0 and t in the tau. This is similar to the one in the previous point A. So if you recall, this integral is t u of t. Cool. In part C, again, both the impulse response and the input are right-sided exponentials, but they are different right-sided exponentials. So now A is different than B. See, x of t is e to minus at times u, and h of t is e to minus bt u. Right, so let's work out the output of the system, again, by calculating the convolution. I write the convolution integral. And as usual, I notice when the step functions are non-zero, and I adjust correspondingly the integral. And now this is the integral I come up with. So this again can be solved by noticing that the first exponential in the integral, e to minus bt, is not a function of tau, so it can be taken out of the integral. And the integral I'm left with is a simple exponential, so it will be given by e to b minus a tau over b minus a, which is the exponent, and this has to be evaluated between 0 and t. So if I do that, this is what I obtain, and this expression can be further simplified to a difference between two exponentials, okay, times a step function. So here's the solution for this exercise. And for part D of the exercise, now this time I'm given the input of the system and the impulse response in this form. So notice that both of them are 1 within a certain interval and 0 otherwise. So to better understand what's going on, I decided to draw these signals. So here's what x of t looks like. It's 1 between 0 and a. And here's what h of t, the impulse response, looks like. It's 1 between 0 and b. And b is larger than a in this case, okay? So if I want to calculate their convolution, I better off write them with a mathematical expression. So now it's easy to do that after we've drawn them. So x of t can be written as u of t minus u of t minus a. Recall we saw this in this very same video at the beginning, okay? And the same thing can be done for h of t. It can be written as the difference between two step functions. Right, so what's the output of the system then? We need to do the integral of x of tau, h of t minus tau d tau, right? So that's the convolution between x and h. So let's do that. That integral will be given by this product between the quantities in square brackets. So this basically will give us 4 different integrals. So I find it convenient to calculate these integrals separately because they are all simple, and then sum up the respective results. So by using the distributive property, I obtain these 4 integrals, right? So let's label them as number 1, number 2, number 3, and number 4. Let's solve them separately and then sum up the result. So we start with integral number 1. Integral number 1 is rather easy. It's very similar to a previous exercise we did today, and we know that the result is simply t u of t. So let's just move on to the ones that are a little bit trickier. Integral number 2 is also not that difficult because it's again the integral of the product of two-step functions. And by just observing when these two-step functions are non-zero, the first one is non-zero for tau larger than a, the second one is non-zero for tau smaller than t, I can rewrite the integral between a and t and obtain the result, which is a minus t u of t minus a. What about number 3? Well, number 3 again is very similar. So again, I use the same approach. I can look at the step functions and see where they are non-zero, rewrite the integral, and obtain something very similar, which is b minus t u of t minus b. Finally, the fourth integral, by using again the same approach, will be rewritten as an integral between a and t minus b in the tau. So of course the result is going to be t minus b minus a when t minus b minus a is positive. So I express this by multiplying again by a step function u of t minus b minus a. So now we're almost done. What we need to do is to sum up the 4 results we have obtained and write a final expression for our output signal y of t. So how to do that? The most convenient way is to just break this down into different intervals. So this is what I'm doing here. I identify different intervals because different things happen in different intervals. Basically, out of these 4 components, some of them are non-zero only in certain intervals. So, for example, when t is negative, all these quantities are zero, so the result is zero. When t is between 0 and a, result number 1 is non-zero and every other result is 0, so the result is t. Between a and b, number 1 and number 2 are non-zero, so as a result I get a. If you sum them up, you get a. And in the fourth range, between b and a plus b, number 1, number 2, and number 3 are non-zero, so if I sum them up, this is what I get, a plus b minus t. Finally, in the last interval, all of them are non-zero, so I need to sum all of them up. But if you do that, you see that the result we get is 0. So here's an expression for our output. If we want to visualize it, well, we can quickly draw it, and we see that this is the shape it takes. Right. So here's the fourth exercise for today and last. So in this case, what we need to do is determine an impulse response h of t such that e to minus t minus 4 u of t minus 4 convolution with this h gives us 2 e to minus t u of t. So how to do that? So I observed that the relation between the input and the output of the system has basically two components. First, that the output is multiplied by 2, so there's a factor 2, right? Second, the output is anticipated with respect to the input by a quantity 4 in time. You see, the input is somewhat centered at time t equal 4, okay? But the output is not, it's centered at the origin. So that means then the impulse response that I'm looking for is something like h of t equal 2 times the delta of t plus 4. 2 is what gives me the multiplication by 2, obviously, by a constant. And delta of t minus 4 is what gives me the shift in time by a quantity 4, because the convolution with the delta shifts the original signal back or forth, right? Perfect. So in this video you have learned about working with continuous time signals and systems through some simple exercises, but because practice makes perfect, I will come back with more exercises in the next videos. I also recommend watching my theory class videos to better understand the fundamentals of signals and systems. Some of the concepts we worked with today have been explained in some of my previous theory videos, for example the concept of convolution and step functions and ideal impulses. And finally, subscribe to this channel if you want to be the first one to know when I upload something new. So see you in the next video.